In today's video, I'm going to talk about how to size an off-grid solar system. I have been living off-grid since 2020 and designed my off-grid solar system for my needs. I want to share everything I have learned through the years, so if you decide to build your own system, I hope this video will help to avoid mistakes and eliminate the extra work. At the same time, you can build a very efficient off-grid system to your needs. Welcome back to my channel Off-Grid with Laszlo and Renewable Energy. Let's start with some questions. What are the electrical loads that you will need to run? Will they run at the same time or you can rotate the loads? For example, if you are using the oven, do you want to use the vacuum cleaner at the same time? By adjusting to minor inconveniences, you can save thousands of dollars not purchasing multiple inverters. Some of the loads will run at the same time, like the washing machine and the well pump or the refrigerator and the stove. That's why your appliance's wattage needs to be checked while you're running. You will also need to pay attention to starting surges for any motors, compressors, so leave yourself a little headroom when choosing the right inverter size. When sizing an off-grid system, follow these steps to find out exactly what will cover your energy needs. Step 1. Calculate your monthly kilowatt-hour usage. How can you do that? Add up your kilowatt-hour usage for 12 months from your electric bill and divide it by 12 to figure out your average monthly consumption. Most people consume more electricity during the winter and summer when the heat or AC is running. Step 2. Calculate your daily kilowatt-hour usage. Divide your monthly kilowatt-hour usage by 30 to estimate your average daily kilowatt-hour usage. If you don't have an electric bill, you can buy this plug-in electrical power consumption watt meter. This device can collect the data for you. The only thing you have to do, plug in an electrical device every 24 hours. During this time, you can check the total power consumption in kilowatt hour, counted time in minutes, frequency in hertz, your voltage, current in amps, and the device consumption in watts plugged in at the moment. The other way we can get this information by checking the home appliance labels for their power consumption. I recommend to get pen and paper and write everything down. If there is not enough information on the label, using this formula we can find it out very easily. Watts equals amps times volts. If any of these values are listed on the plate, we can find the third one out very easily by plugging the numbers in. For example, your home probably have much more appliances that I'm listing right now that draw more loads as well. For off-grid systems, an inverter converts DC to AC power and always consumes a small fraction of generated power when running. Let's assume my inverter uses 70 watts and runs for 10 hours a day. We need to add that to our power load. Also, we have to account for inefficiencies in our overall system that usually ranges between 5 to 15% and depends on the type of the inverter we use and how much load we draw. In order to compensate that, we need to oversize our battery bank. This is quite an important step to consider when sizing our system, so make sure not to skip it. Step 3. Calculate the size of the battery bank. We can use different types of batteries to store energy lead acid, AGM, lithium ion, but not properly designed systems are going to fail. The size of our battery bank will depend on the amount of backup power we will require to run our appliances. You may find that in the winter months, it makes sense to add a backup solar generator to your off-grid system because may not enough sunlight to power your home's solar system. Your first step is to decide what battery voltage you are going to use in your off-grid system. In most scenarios, the battery's output voltage will be rated for 12, 24 or 48 volt. 12 volt, perfect for smaller solar systems, 24 volt, good for medium, and 48 volt, the best for large solar systems. Take a look at your inverter spec sheet and see what the efficiency rate is. If it is 90%, you will of course have to add 10% to your daily load sheet. Next, account for temperature fluctuations. Temperature fluctuations affect battery efficiency. You should expect batteries to become less efficient in winter. Both lead acid and lithium ion batteries operate at varying efficiencies in colder weather. Lithium ion batteries tend to operate at a better efficiency in winter. Let's use lithium batteries in our example and multiply our battery capacity by 1.2. If you use lead acid batteries, multiply your battery capacity by 1.6. We also have to account for efficiency loss when charging and discharging batteries. Efficiency loss for lead acid is 20% and for lithium ion is 5%. Additionally, you have to decide on days of autonomy. Autonomy is the number of days the battery bank can power your loads without being recharged. This should be between 2 to 5 days. Now multiply your battery size by the number of days you want. In this example, we will use 3 days. I am sure you have already noticed temperature changes, inefficiencies, and battery type make a major difference on the overall size of your required capacity. To convert from watt hours to amp hour, simply divide the battery capacity by its voltage. Keep in mind that you will need to account for your battery's depth and discharge rates. For lead acid, it is 50%. For lithium batteries, 90 to 100%. If you plan on building lead acid system, you will essentially need to double your required battery capacity in order to have the correct capacity. Otherwise, batteries will degrade too much within a very short time. I want to tell you again, this is an example and your home probably have different loads, more or less appliances. There is a lot of way to save energy and the backup generator can make a big difference as well. To oversize a battery bank always suggested, I really recommend to buy the same brand and amp hour batteries, especially if you want to have a closed loop communication. There is one more thing I want to add to this part. Even though our battery bank in this example is 3283 amp hour, let's multiply this number by 0.9 and we can get the amp hour we are able to take out from this battery bank to our loads. After we have correctly sized our battery bank, we need to figure out how much power we are going to need to recharge it. Before we do that, let's talk about what is a solar panel. A solar panel is a photovoltaic PV module that converts sunlight into direct current DC energy. This energy then flows into an inverter, converting it into alternating current AC energy that can be used for power homes. Solar panels rely on the sun energy, making them an incredible, sustainable and eco-friendly energy option. To make the most of use of solar panels, here are some calculations to consider before you invest in them. Step 4. Estimate the amount of sunlight your solar panels will receive. Sunlight availability affects how much energy your solar panels generate. average peak sun hours depending on your location and your local climate. Look up your peak sun hours through a sun hours chart or a map like this so you can make the most of your solar power. This map is from National Renewable Energy Laboratory. Take the calculated battery bank watt-hour from step 3 and divide it by the number of sun hours in your location. For example, in Texas where I live, we get about 5 sun hours per day. Now let's talk about solar panel efficiency. The efficiency of solar panel refers to the amount of sunlight that is converted into usable energy. Panels with higher efficiency are able to generate more power from the same amount of sunlight. Most of the time, this value is listed on the website, like here, but if it's not, this is how we calculate it. First, we have to calculate the solar panel area in square meter. In order to do that, let's multiply the solar panel length and the solar panel width. Most of the time, this information is listed in inches, so after we multiply these two numbers, we will get the number in square inch. For example, there is this 400 watt panel. Measurements are 67.8 inch long, 44.6 inch wide. Once we multiply these numbers, we're gonna get 3023.88 square inch. Let's divide this number by 144. We're gonna get close to 21 square feet. And once we divide this number by 10.764, that's gonna be 1.95 square meter. The efficiency is calculated by this formula. Efficiency equals solar panel max output divided by solar panel area in square meter divided by 10. Once we plug these numbers in, we are going to get 20.51. That means the solar panel can convert 20.51% of sunlight into usable energy, and we are compared to this value to the one on the website, we are really close. Step 5. Account for inefficiencies. We need to add a little bit of overhead to account for inefficiencies and degradation rate of the panels. The output of solar panels drops slightly each year. If your solar panels performance warranty guarantees 80% performance after 25 years, then the degradation rate is calculated as 20 divided by 25, or 0.8% production loss each year. A 400 watt solar panel would only output 320 watts by the end of its life cycle. So let's take the calculated solar array size from step 4 and divide it by 0.8. In addition, solar panels are tested in idle conditions. In the real world, solar panels often produce a bit less power than the wattage rating. Because of these factors, it's wise to buy extra solar panels so you can reach your target production figures after accounting for inefficiencies of the system. 10% is a good amount of headroom to account for inefficiencies. Multiply your solar array size by 1.1. Step 6. Determine how many solar panels you need. Once you have your final array size, simply divide by the wattage of your desired solar panels to figure it out how many panels you need. Let's calculate using this 400 watt rated solar panel. For this array, we need 108 solar panels. Step 7. Solar inverter sizing. An inverter's primary task to convert DC direct current generated by solar panels to AC alternating current. Solar inverters are the brains of the operation when it comes to the solar systems. The inverter is the central meeting point for the solar panels, battery power, and sometimes the generator port as well. The inverter controls the power flow to various solar system components while also having a critical task to converting DC to AC. Solar inverters are rated according to their maximum output. like a 6 kW inverter will deliver 6000 watts of AC power, and the 12 kW inverter will deliver a maximum of 12,000 watts of AC power. The priority is to select an inverter that comfortably power the selected electrical circuits in the home, while running at the same continuous power rating and charge the batteries with a reasonable time from the power generated by the solar panels. The charge controller, or MPPT, controls the energy that flows into the inverter. The charger, or MPPT, carries the rating specified in watts and amps, which will determine the maximum size of PV array can accommodate. Most hybrid inverters would contain an MPPT or multiple MPPTs rating up to 600 volts and 200 amps. So, how do we choose the right inverter? First, let's check out the solar panel specs. Wattage 400 watt, VOC open circuit voltage, which is the maximum voltage a solar panel can produce when it's not connected to a load. And the other information we need from this spec sheet is the ISC, which stands for the short circuit current. This is the maximum amount of current a solar panel can produce. Now let's check out the inverter specs. There are 3 MPPTs and the max usable input current on the first MPPT is 25 amp, on the second and third is 15 amp. DC input voltage range is 100 to 600 volts. We know the panel's open circuit voltage is 37.21 volt. Now we have to multiply this number until we are around 500 volt. Connecting panels in series, we call it a string. If we connect panels in series, we increase the voltage. If we connect them in parallel, we increase the amps. So let's connect 13 panels in series, and the voltage will be around 484 volt. And let's multiply 13 by 400, and we're gonna get 5200 watt. Since the short circuit current for this panel is 13.67 amp, we can connect 2 strings in parallel for the first MPPT and 1 string to the second and third as well. In this example, our total wattage will be 20,800 watt, and if we multiply the panels by the number of strings, we know we can connect 52 panels to this inverter. If a 12 kW inverter is enough for our needs, we can buy a large charge controller and connect the rest of the panels to that. Another option is to buy an off-grid system based on your budget. You always can start in small and expand it later for your needs. However, if you choose this route, there are going to be a lot of extra work involved. I suggest you to be very careful before purchase anything. I already have an inverter that can't deliver the power that's on the spec sheet, and I have a battery that works really well, but the company is out of business. Unfortunately, we can look at the spec sheet warranty information prior to purchase, but no guarantees on that. These days, we have much more options to choose from than a few years ago, and the sooner you start, the more money you can save. Please check out my videos by clicking on them in the description. This is all I wanted for today. If you have any questions, let me know in the comments below. Please subscribe to my channel if you haven't done it so, and you will get a notification about my upcoming videos. Thank you very much for watching, and see you in the next one.